linear independence and dependence. But there are a lot of unanswered questions. So for example, suppose I tell you that V1 up to Vm is a linearly dependent list. So that means that there exists field elements, matching field elements A1 up to Am, such that the sum from I equals 1 to M of AI Vi is a non-trivial expression for 0. So if this is equal to 0, then not all the AIs are 0. So this is a shared property, right? This is a property of this entire list of vectors. And what's unclear is whether it's kind of the fault of any one particular vector in this list. Can I blame this dependence or this failure to be independent on any one vector? And if I did find a vector which was somehow the most dependent or the worst, or just a vector that I could blame for the linearly dependence of the whole list, and I take it out, what happens? Am I guaranteed to be left with something that represents everything? And if you think about it for a minute, you'll feel okay that you can do that, but okay, we haven't proved it yet. So the other sort of mystery is we don't know how many linearly independent vectors can fit in a vector space. And if I give you a vector space and I start choosing vectors, choosing another vector which is independent of that, and so on, how long can I do that for before I run out of freedom? I run out of new directions and I'm into the dependent situation. And this is kind of a natural measure, some kind of measure of the size of the vector space, right? How much independence can be fit into that. And related to that question is we've been talking about dimension, finite and infinite dimension, but we don't know yet what is dimension. What is the dimension of a vector space? We know how to say it's finite dimensional, we know how to say it's infinite dimensional, we don't know how to give it a number, like it's three-dimensional, except sort of intuitive arguments about parameters. Okay, so today we're going to talk about some ideas that answer this question and start to answer these questions. And the first is this lemma. So in the book, it's called the linear dependence lemma. And I kind of like to call it the scapegoat lemma. So if you know what a scapegoat is, if a group of people is responsible for something, climate change or something, and nobody wants to admit to it, we pick some person who's the unlucky person, who's the scapegoat, and it's their, we decide that it's their fault, even though it really is all of our faults. So linear dependence is a little bit like that. It's a property of the whole list of vectors, but it's possible to choose one vector that's kind of the scapegoat. We pick a vector that's dependent, we can throw it away, we can kill it, and that's the point of this lemma, just that it's possible to do this. Okay, so suppose V1 up to Vm is a linearly dependent list. Of vectors. Vectors in V. And further, suppose the first of these vectors is not 0. They're all 0. This is really stupid. So this is kind of just a technical. We're going to pick one of them that's not 0. Then there exists a particular j, an index in the numbers 2 up to m. So there exists a particular j such that Vj is my sort of scapegoat vector. This is not part of the lemma. That is, it satisfies two properties. One, this Vj is contained in the span of of all the vectors that come before it in the list. That's the first bad apple, right? The first redundant vector. There's a notation for span that I like, which emphasizes that what this sequence is, which is we could say span of V less than J. That's just the V's that have the index 1 up to J minus 1. And the second thing is that it's okay to get rid of this vector, right? We've made it our scapegoat, we can kick it out of society, and we still can function. If we remove this jth term from the list, what's left has the same span. That is the span of, so here's another notation, V1 dot 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 Vj, and I'm going to put a hat over Vj. That means the little hat here means delete that one from the list. Up to Vm is equal to the span I started with, the span of everything including Vj. Span of V1 up to Vm. Okay. So I'm saying it's like a scapegoat lemma because it doesn't say there's any one particular vector that's to blame for the linear dependence. That's a shared property. What we're saying is that we can choose one. We can choose sort of a particular vector, throw it out. It's in the span of the things that came before it, and throwing it out doesn't affect the span of the list. Okay. Now, you see the word lemma here. So a lemma, remember, is something typically that we don't really care that much about it, but it's handy for proving other things. So that's the situation here. This lemma is not so exciting, but it will make other arguments that we need to make, especially in the next couple of weeks, much faster. So that's why it's a lemma. Okay, so let's prove this lemma. It's a bit of a long argument. Part of the reason that I want to make it long is because I want to be detailed about the way that I explain it. Okay, so we start out with the hypothesis. So we have this list, which is linearly dependent. And we have this property that the first one is not the zero vector. By definition, this means there exist field elements, AI and F. They're not all zero, such that this linear combination, I sum from I equals 1 to m, AI scalar multiplied times the VI is equal to 0. So we have a non-trivial expression for 0. Okay. So we're looking to pick one vector out of the list. So the next thing we're going to do is to find, among all these coefficients, a guarantee that some of them are not 0. Okay? And that's sort of what we use this first assumption for. So VI is non-zero. It's not the zero vector. Suppose that A1, its coefficient, the coefficient of the first vector, was equal to 0. Then because these are not all 0, it must be that some that coefficient A2 up to AM is non-zero. Okay, that's what we want to show, that these are not, that there's some additional non-zero thing in what's left over. On the other hand, if A1 is not 0, V1 is not 0, so A1 V1 is not 0. So our expression here is going to look like A1 V1, which is something which is not 0, plus other stuff equals 0. So it can't be that this stuff is all 0, right? Because something has to cancel this. Additive inverse, right? This stuff is the additive inverse of, when I move it over here, minus stuff becomes the additive inverse of A1 V1. So there better be something there. So this is not 0, that has to be not 0 too. In particular, that means that in this case also, some a2, some one of these coefficients is non-zero. Because if they were all 0, then this would be 0, and it couldn't be the inverse of something non-zero. Okay. So from among these, we're going to pick the j that we want to pick on. So let's let j be the largest j. So the last term, the largest j in 2 up to m, which has the property that a sub j, the coefficient, is not 0. Okay. So it's the last non-zero coefficient in this linear combination, ordered as we've chosen it. Okay, what does that mean? Well, we can write aj vj just by subtracting, using the additive inverse of all of the things other than j in this expression, moving it to this side of the equation, which we now know we can do. So that's equal to a1 v1 minus a1 v1 minus a2 v2 if there's a 2, and so on, up to aj minus 1 vj minus 1 minus. Okay, but I claim that I can stop here. So why can I stop here? Because this was the largest one that was not 0. So all the rest of them are 0. So that's why I'm stopping. Okay. Also, we know that aj is not 0. That was what we were doing here. So what can we do with things that aren't 0? We can divide by them. Right, vj equals minus a1 v1 divided by aj minus a2 v2 divided by aj minus aj minus 1 over aj vj minus 1. Great, okay. So that's the first part, right? We showed that vj is in the span of v1 everything except vj. Vj is in the span of all the other vectors. Of the up to the preceding vectors. Vj minus 1. Vj minus 1. The rest of the stuff I can ignore because it's okay, 0. So vj is in the span of v1 up to vj minus 1. I wrote v less than j. Then we want to show the second part. So for the second part, we want to show that the span that we began with, the span of the entire list, is unchanged by deleting v. Deleting vj, right? So you can sort of see why that's going to happen. But let's, to prove that, let's pick something. So suppose u is a vector that's in the span of v1 up to vm, the list that we started with. So u expanding, u equals c1 v1 plus dot 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 up to c MVM. Somewhere in there is uj, the cj vj. U equals, so somewhere in the middle here, up here is a cj vj, whatever the constant was that multiplied vj. And now we have this other expression for vj, so we can just substitute. So u equals c1 v1 up to cj. And instead of vj, we can put this whole thing, minus a1 over aj, v1 minus A2 over AJ, V2, and so on, up to minus 8j minus 1 over AJ times V j minus 1. And whatever other stuff, we don't really care. Okay. So there could be other vectors in here. The important thing is that we're substituting. Okay, so manifestly, every vector that appears in this thing, in this expression, is in the list minus Vj. So we haven't changed the span. We've shown by construction, if U is in the span of this, it's expressible as a linear combination of the whole list. It's expressible as a linear combination of the reduced list. So now let's use this lemma, which I said was handy to prove some things about the other questions. My second question was, how many linearly independent vectors can I cram into a single vector space as a measure of the size of the vector space, so we can get at least some kind of an upper bound using what we've developed so far on that number. It's theorem 2.6 in your book. And let V be a finite dimensional vector space. What's the definition of a finite dimensional vector space? It's a vector space which has a list, a spanning list, which is finite list. Let V be a vector space which has a finite spanning list. And the length of any linearly independent list of vectors in V is at most, meaning less than or equal to, the length of any spanning list of vectors for V. So every spanning list gives an upper bound on the number of linearly independent. Any spanning list that if I give you a list of size 10, it's a spanning list, then I can only cram at most 10 linearly independent vectors. Then if I found a spanning list of size 8, then I know that in fact I can only put in a list of size at most 8, and so on. Okay? But we haven't said yet how to show that all of these things are going to be the same, but this is sort of an upper bound. Every spanning list provides an upper bound. Prove that. So this is going to be kind of an induction or a substitution argument. Okay, so our inputs to this are two lists, right? We have U1 ... up to UM. This could be our linearly independent list. And we have W1 up to WM, N. The first one is M, and the second one is N. This is a spanning list. And our goal, what we want to show, is that M is less than or equal to N. This list is no bigger than that one. So we're going to do this with sort of a base and induction. So our base, our step 1. We know that our spanning list, W1 up to Wn, spans V. Definition. We don't know if it's linearly independent or dependent yet. Right? Point already linearly dependent. But it's a spanning list. Everything in V can be expressed in this. So certainly if I add another vector to it, then it will become dependent. Because this new vector can be expressed as a linear combination of the others. Subtract the new vector minus this expression, and you get a non-trivial expression for 0. Okay, so if I add a vector, it becomes dependent. So we'd like to add, in particular, let's add the first vector from our linearly independent list. So U1, W1, W2, so on up to Wn is linearly dependent. So this one comes from the independent list, and these are the spanning list. Okay, so now we use our lemma. By our linear dependence lemma, or our scapegoat lemma, we can choose a particular vector in this list such that the new list, losing one of these vectors other than the first one, still spans the space. Okay. So the linear, if we want to apply our lemma, it had another hypothesis, right? The other hypothesis was that U1 is not 0. So how do we know that U1 is not 0?
It's part of the linearly independent list.
Yeah, so this is part of a linearly independent. So if U1 was 0, right, if my list was 0, let's say it was 0, U2, I can construct a non-trivial expression for 0, which is 1 times 0 with U1 plus 0 times U2. And now I have a expression for the 0 vector. But not all entries are 0. Okay, so this first vector can't be, in fact, none of these vectors can be the 0 vector in a linearly independent list. Okay, so that's okay. We can apply the lemma. So we can choose a particular one such that choose WK to throw away. So that U1, W1, whichever one we threw out, Wn spans V. That was the first step. We continue with more steps like that. Suppose now we've performed J minus 1 steps, beginning with J equals 2. Suppose we've performed J minus 1 steps. At this point, our list looks like, where we've made substitutions. Well, after the very first step is just U1 and then some W's, but after we did some other number of these, we go up to J minus 1, and then we have left over some W's. And this list, the list from step J minus 1, spans V. And adding another vector, well, let's say adjoining another vector, makes it dependent. So now we have a list that looks like U1 up to Uj minus 1, Uj, and some W's. We added this one. And then we find a vector which is expressible in terms of the others. The first ones are linearly independent, so this is going to come from out here. Delete the wk can be expressed in the span of the things that come before it. All right, that can't happen in this list because these are all linearly independent. So none of these will be able to be expressed in terms of the ones that came before it. The first time that can happen is when we get into the W's. So we delete. So there's something in here that's redundant, or we can choose something to be redundant. We get rid of that one. And then we're left with a list. It has length n, and it spans v. So we just keep doing that. We keep to do that until we run out of u's. So we started out with u1 up to um. So after step m, all the ums have been inserted. Uj, ui have been added. And at that point, we stop. And what we want to argue now is that it must be that, the number of w's left over is at least 0. If that's true, then m is less than or equal to n. Yeah. A slightly more sensible way of saying that is to say that if that were not true, at some point we would have gotten to a situation where we had the u's inserted, and there were no w's left to take them away. There were no w's left to be deleted as dependent on the rest. But that would mean that we would have a contradiction to the linear dependence lemma. That is, we would have a linearly dependent list, this intermediate list. And it has no element, even though it's literally dependent, it has no particular element that can be deleted. It couldn't have been among the u's because they don't satisfy this. They can't satisfy this span of the preceding vectors property, so it must be among the w's. So it would have been a contradiction. Okay, so then we know that the number of w's, is at least number of u's. Let's fail. Well, let's say something. We can't quite get to dimension yet. We will probably next time, or the class after that. But we can say a little bit more. We can say that every subspace of a finite dimensional space vector space is itself finite dimensional. And the proof is a similar argument by induction that makes use of this linear dependence lemma. So suppose U is a subspace of V, which is finite dimensional. Remember, though we don't know how to count dimension yet, we know that something is finite dimensional if it has a spanning list, which is finite as a list. base of our argument, or our step one, will be to consider the case that U is the zero vector space. So that one is spanned by the empty list. It's finite dimensional. If it's not, if it's bigger, it's not zero, we can choose some vector in U which is not zero, not the zero vector. And our induction step, or our steps 2 through J, well, if we're done, we're done. If U is in the span of all the vectors we chose before, V1, whatever that was, and then we chose some more, V2, and so on up to Vj minus 1, then we've proved that it's finite dimensional. If U is not equal to that, since all these vectors lie in U, U must be bigger than that in the sense that there must be some vector in U which is not in this span, and which is not zero. So choose some Vj in U such that Vj is not in the span of V1 up to Vj minus 1. So then in each of these steps, in each of these induction steps, we're in the situation that we have a list of vectors and no vector is in the span of the vectors that came before it in the list. That's how we constructed it, right? No Vk is in the span of V less than k. That is the span of vectors V1 up to V k minus 1. So by the, again, by this contrapositive, actually, of the linear dependence lemma, or the scapegoat lemma, this must be a linearly independent list. Otherwise, I could choose something that would have this property. Linearly independent list. And by the other proposition we have, this list can't be longer than any spanning list. For V. For V. And V is finite dimensional, so this number, so V has a finite spanning list, so therefore U must have a finite spanning list.
What is it that U is not equal to?
U is not equal to the span of V1 up to Vj minus 1. So we use Okay, so the last problem in your homework is about bases. Bases, basis of a vector space. So I should at least give you the definition of that before we go. definition, the basis of a vector space is a special kind of list. List of vectors in V it has two properties. It's linearly independent. And secondly, it spans V. None of them are dependent on each other, and yet they're enough. It's necessary and sufficient. For example, if my vector space is the infinite blackboard, the kind of Cartesian coordinates would be a good choice of basis. But there's nothing special at this point about that. That's an equally good choice of basis. So is that. What's not a good choice of basis is if the only thing that can sort of go wrong here is that the two vectors are multiples of each other, so that's not a basis. Not. The other thing that can go wrong is that I have too many vectors, such that any one of these could be expressed as a linear combination of the others. They fail to be linearly independent, though they span. This one is not linearly independent and does not span. This one is linearly independent and does not span. If I think about 3 dimensions, then all of these fail to be bases because though some of them span and some of them are linearly independent, though some of them are linearly independent, none of them span the space that includes all 3 dimensions and coming out of the blackboard. The last thing I want to mention is one proposition. That connects it to what we've been saying about direct sums and decompositions. That's this. List V1 up to Vm of vectors in V. Is a basis of V if and only if every vector in V can be written. So it spans if every vector in V can be written as a linear combination. But it's a basis if it can be written uniquely as a linear combination. Of vectors in V in this list. AI, of course, in our base field. And VI is coming from the list. So I want to stop there, and we'll continue with some more facts about bases and the definition of dimension.